Okay, very good. So hopefully today we're going to finally get to do the Rankine-Hugoniot mathematical, let's say, description of combustion waves, okay? And we'll see whether we can recover these two families of solution that I've anticipated on Friday, deflagrations, which are the subsonically propagating solutions, and detonations, okay? So first of all, let me rewrite the jump relations, okay, in the general form. Which are respectively conservation of mass, okay? So remember what the jump operator is, conservation of momentum, okay? This is the normal component of momentum. Now, there is also a tangential component, but as you can recall, we're doing a one-dimensional analysis. So we are considering the tangential component to be zero, okay? So we are going to neglect this, okay? And then finally, the conservation of energy, okay, across the interface. Which is essentially the conservation of total enthalpy. Now, another thing that we can remember is that we prefer the wave stationary reference. So essentially, we have a wave here, okay, with a normal propagation speed, which is identically equal to zero. This is the wave stationary frame, right? This is what we are going to write those jump relations in the frame in which we're going to write the jump relations. We have a plus and a minus side, respectively indicating the unburnt and burnt side, okay? The fresh and burnt side. So we have a normal velocity on the plus side, okay, which we have defined as u, okay, the unburnt, and then the normal velocity here on the, on the minus side, we called it ub, okay, the burnt side. Now, we also recall that Vn, okay, by definition is the flow velocity relative, okay, to the interface, okay? So by definition, this is the normal velocity, the absolute normal velocity minus the normal propagation speed of the interface, okay? Now, we can define this velocity on the plus side as well as on the minus side. Okay, and clearly because essentially Wn is zero, the definition is really straightforward, okay? They're essentially u, and ub, okay? So this is the velocity of the flow relative to the interface is nothing else but the actual velocity, u on the plus side and ub on the burnt side, okay? Why do we need to define these Vn plus and Vn minus? Because they appear in the jump relations, okay? So now we can finally substitute, okay? We will unfold, okay? Remembering that the operator is essentially, if this is psi, it's psi on the plus side minus psi on the minus side. So we will unfold all these operators and substitute for Vn plus and Vn minus. What we get is something like this. So we have rho u U, okay, on the unburnt is equal to rho B U B, which is pretty obvious, okay? The mass flow per unit area must be conserved, okay? We can call this mass flow, essentially, we can give it a name, which would be F or M dot, doesn't matter, okay? Let's look at the normal, okay, component of the momentum. That is rho U, U squared plus P U is equal to, so this is the conserved quantity, rho B U B squared plus P B squared. Sorry, PB, not PB squared. So that's the conservation of normal momentum, and clearly for the conservation of energy, we have essentially that the total enthalpy is conserved, okay? So it's pretty straightforward, okay? But we rewrote this, let me just rewrite it again here in a wave stationary frame, okay? Now, we're going to have to solve these in some way, okay? Now, there are many ways you can do this. The most sort of straightforward, the best kind of way of doing this is graphically, okay? And I'll show you what I mean in a second, okay? But the long story short, we will set up a plane. For example, a plane, it could be rho P, or for example, in this case, we're going to choose the following plane: pressure, okay, on the the specific volume, which is 1 over density, okay? So we're going to essentially choose this plane, and we're going to represent these three jump relations as curves, okay, on these planes, okay, on this plane. And obviously intersections, okay, of these curves will give us essentially points where the three jump relations are satisfied simultaneously, okay? So points, intersection points are going to be the solution of our jump relations. So in some sense, they will represent combustion waves, okay, that actually guarantee the conservation of mass, momentum, and energy. We're going to essentially solve those three graphically. So how do we do this? Well, the general technique here is to draw what are called the Rayleigh lines. At least that's what you will see them defined in the classical text, okay, in the classical textbooks. So these essentially represent curves which guarantee the conservation of mass and momentum. So the first two relations, the first two jump relations here, okay, these are the Rayleigh lines. Let's short for Rayleigh lines, let's put an R here, okay? Let's see how we proceed, okay? Every now and then I will sort of jump a few steps because they're really straightforward, okay? So there's no difficulty there. But just for the sake of conciseness, okay? So let's start with momentum. Okay, we will rewrite this in the following way. The difference of pressures, okay, is equal to essentially rho U squared minus rho B UB squared. We can rewrite this essentially by factoring out rho U all squared which multiplies essentially 1 over rho u minus rho b ub squared over rho u squared. Long story short, we're then going to use the conservation of mass, okay? Rho u is equal to rho b ub, right? So where do we use the conservation of mass? Well, we use it for this term here, okay? And it's quite easy to prove that this is very simply 1 over rho b, okay? So you can do this yourselves, okay, by using the conservation of mass. So at the end of the day, we're going to have that pb minus pu is equal to rho u squared, okay? And then very simply 1 over u minus 1 over rho u minus 1 over rho b, okay? We called this, the mass flow here, F squared. So we can rewrite this as the following. We can put a minus sign, okay? F squared, and then these are 1 over, densities are in fact specific volumes, so we can write down VB minus VU, okay? And F is measured in essentially kilograms per meter squared per second. So it's essentially a mass flow per unit area. Now, this is what, so the important step that will define our plane PV. I said at the beginning, we're going to use PV. In fact, it's much better if we use non-dimensional quantities. So I'm going to define these two non-dimensional variables, okay, which is the non-dimensional pressure. I'm going to use this sort of P hat here, and I'm going to define it as PB over PU, okay? And V hat, okay, is going to essentially be VB over VU, okay? So my plane of interest is going to be PV. So I simply now want to express my Rayleigh lines, which represent essentially conservation of mass and momentum, okay, on this plane here, okay? Let's see what we can do. Well, of course, I can factor out, for example, PU, okay? So I'm going to have P hat minus 1 here. Then I have this F squared, which is rho U squared, okay? Then I can factor out VU, and then I have V hat minus 1. So at the end of the day, this P hat minus 1, okay, will be equal to a quantity which is essentially UU squared divided by, remember that rho U is 1 over VU, okay? So at the end, we have something like PU over rho U, okay? And then V hat minus 1. Okay, so it seems that we have reduced the complex of conservation of mass and conservation of momentum across a moving interface into one linear, essentially, equation in the variables P hat and V hat. Now, it's also interesting to see what this term is, because indeed, if you look at the definition of Mach number, now this is the Mach number in the unburnt side. So remember, we are in a wave stationary frame of reference. So the wave, the combustion wave, is stationary, and we're feeding fresh mixture, okay, at a velocity u. So there's also going to be an associated Mach number to that velocity of the fresh mixture, which by definition is essentially u divided by the speed of sound. Now the speed of sound in the unburnt, okay, side. So it's au, okay? So as we know, it's the square root, okay, of gamma r tu, right? Where tu is the, you can still hear me, right?
Sì, sì.
Okay. Can you still hear me? Because I'm always afraid of touching stuff.
Sì, sì.
Sì, sì, prof.
Now let's use the equation of state for ideal gases, okay? Down here, so we have the square root of gamma, and then essentially RT is PU over rho U, right? So that means essentially that this quantity here, uu squared divided by Pu over U rho U, is nothing else but gamma and then the Mach number squared. So we have a very convenient form of the Rayleigh lines, okay, which is the following. So P hat minus 1 is equal to minus gamma, and then the Mach number of the propagate. This is, again, remember, the Mach number mu is the Mach number of the fresh mixture, okay? But it is also, okay, in a wave, in a laboratory frame. Remember, how to switch from one frame to the other is really simple. You just subtract u, essentially, to both the upstream, the downstream, and the propagation speed, okay? And so you will have in the laboratory frame, you have a quiescent mixture. So the upstream is 0, and then you have essentially a propagating flame propagating at minus uu, okay, speed. So essentially mu is also the Mach number, okay, of the flame itself, okay, in its propagating motion in a laboratory frame. So I hope that's clear. So this can be thought of as the propagating speed or the propagating Mach number, okay? Now look at how simple this this relationship here is, okay? I would also would like to remind you, if I haven't said it very early on, when we derived the jump relations, if you remember, we neglected a series of things, well, viscosity, things like that. But most importantly, we have neglected any heat flux exchange of heat with the surroundings. So it's like Q dot equals 0. Remember that? So we are effectively in an adiabatic, okay, configuration setting. So this system, okay, doesn't lose, okay, heat to the surrounding, okay, which is quite important. So let's look at these quantities here. So we said that we were going to use this plane, so let's use it. So we are in this plane here, okay? So let's have V on the x-axis, V hat, and P hat on the y-axis. Now, first of all, if you look at this linear function, okay, these are all slopes, these are all linear relation, so they are straight lines passing through the point 1, 1. Okay. So what's the special? What's so special about this sort of 1, 1? Well, remember the definition of P hat and V hat. Okay. So essentially, 1, it means essentially that PB is equal to PU or VB is equal to VU. So what we can say morally is that this point here can uniquely identify, for example, the upstream conditions, okay, if you will, okay? So this will appear extremely clear when I draw the lines. Now look at this slope. Now obviously the Mach number here, this is always a positive. It doesn't matter whether it's subsonic or supersonic, okay? It's always positive. So there's a minus sign here. So it seems that these curves, irrespective of whether the Mach number is supersonic or subsonic, they're always having a negative slope. So that means that they're either lines like going like these, okay? And this is the case where mu is supersonic, so it's bigger than 1, okay? Or they're lines that are like this when mu is less than 1, okay? So the bottom line is this area here is really forbidden, okay? This and this area here. Why? Because if the line went through the forbidden area, the slope will be positive. So again, mu can be thought of the upstream Mach number in the wave stationary reference. And 1, 1, this state here, okay, this dot here, can be thought of as the sort of upstream state. So what does that mean? It means that all downstream states, okay, that are compatible with the conservation of mass and momentum, they all lie on these lines. So for example, there are somewhere here or somewhere here, okay? Bear in mind that there are infinite states at this point, okay, that conserve mass and momentum. Whatever point I choose on these lines, okay, they conserve mass and momentum, okay? But we can already say something very, very important, okay? So now any point here, okay, will be a point PV, okay, which will represent PB over PU and VB over VU, okay? So for example, if I give you the upstream conditions of pressure and density or specific volume, this point here will uniquely identify the downstream PB and VB conditions, right? And they will do this for a supersonic combustion wave or a subsonic combustion wave. So we have essentially two possible scenarios, okay? One where the Mach number upstream is subsonic. So we have a subsonic combustion wave, okay? So you have to look at these lines here. Now, if you look at these lines, okay, you will see that, well, the slope here is very shallow, okay? So if we move along this line, you'll probably see that what the dominant variable here is the specific volume, in the sense that because the slope is very small, okay, as I go along these, as I move along this line, it's really the increase in V hat, which is the dominating aspect, and not the decrease of pressure, right? On the other hand, look at this other line here, the supersonic line, okay? It's quite the opposite. I mean, this decrease in specific volume is actually much less than the increase in P. So when P hat, so for the supersonic solution, it's really this aspect, the P hat, which essentially is the dominating aspect. So what does this mean? It essentially means that for subsonic solutions, it seems like we have essentially a dramatic decrease of density. Okay, remember that. Remember the definition of V hat is VB over VU, so it's rho U over rho B. Okay, and we can assume very roughly that the pressures are more or less the same. It's not totally true. There's going to be a decrease in pressure, okay? But especially if the Mach number is very small, okay? So I could even add here very small, okay? And this is usually the case, by the way. I will spoil a few of the things we're going to say, but this is definitely true. So we have a family of subsonic combustion waves for which the dominating aspect is thermal expansion, okay? So the decrease of density. But this will happen essentially at constant pressure, okay? And this is the typical situation of deflagrations or premixed flames, okay? We know that they're subsonic. And we also know that they're essentially isobaric processes, okay? On the other hand, if you have a supersonic solution, okay, what seems to be the case is that the burnt pressure is much larger than the unburnt. So these seem to be, so these supersonic solutions seem to occur with, or seem to be associated with, an extreme compression, okay, downstream. On the other hand, the density, well, can increase, okay? It's obviously like this, but the dominating aspect is this, whereas for deflagration, the dominating aspect is this. So these will be the characteristics of detonations, and these will be the characteristics of deflagrations. So we have already understood that we don't yet know where we are, okay, on this graph, whether here or here. We don't know this, but undoubtedly, these will be the characteristics, okay, of these two families of curves, okay? Good. Now, where are we on these curves, on these lines? What points, and how many points, in fact, will conserve mass, momentum, and energy, okay, will be revealed by the conservation of energy, which we have not used yet. Now, conservation of energy okay, will essentially lead to another curve in the PV plane. I hope it's clear, right? Everything is is straightforward until now, right? Can you hear me?
Sì, sì, tutto bene.
Okay. It will be given to us with yet another curve, which is the Hugonio curve. So these are the Rayleigh lines, the ones we've just seen. Now we're going to derive the so-called Hugonio curve, or simply the Hugonio, by using the conservation of energy. So the jump here relation that expresses the conservation of energy, okay, we wrote it many times. Oh, and of course, I get it wrong. Is like this. So we do something similar to before. We try to rearrange. Oh my God. Okay, I'm gonna do this many times. We try to rearrange this conservation of energy. So the difference in static enthalpies will be essentially 1/2 of UU squared minus UB squared, right? So I can, for example, I can factor in out UU, okay, squared, and I'll get 1 minus UB squared over UU squared, okay? What we can do here, we can also multiply by, because we want to have the mass flow per unit area up here. So we can multiply by rho u squared divided by rho u squared, of course. And we can have, so the left-hand side stays the same, and also the right-hand side, but we'll get something like this. So rho u squared, which is the mass flow, and then 1 over rho u squared, and then minus ub squared over u squared. Okay. And remember that we also know that rho u is equal to rho b, okay, ub, from mass conservation. Okay, so in fact we are also using the mass conservation here. HB minus HU, okay, will therefore be equal to 1/2 rho u squared, okay, and so we substituted in here, okay, rho b ub, so we get essentially rho u squared minus 1 over rho b squared, okay, which is something like minus 1/2 f squared, and then vb squared minus vu squared. As you can see now, we don't have a linear relation anymore, okay? In fact, we can write down HB minus HU, okay? We can expand this, okay, as minus 1/2 f squared, and then we have VB minus VU, and VB plus VU. Okay? Now, let's go back to the Rayleigh lines for 1 second. because we had an expression for, if you look up here, for VB minus VU, okay? Which appears here. So I'll write it out right here. I can't write with this thing. So the Rayleigh lines told us that PB minus PU is in fact equal to minus F squared VB minus VU, okay? And so what we can do here, we can rewrite HB minus HU, okay, is equal to, now plus, okay, 1/2 VB minus VU, okay? And then we substitute for this VB minus VU, we substitute PB minus PU, okay? Okay, so this is one of the sort of semi-final state of the Hugoniot lines. Now, clearly, it's not very useful.
Professore, scusi, ma è VB meno VU o VB più VU nell'ultima equazione?
PB meno più.
No, VB, il volume. È la somma dei volumi o la differenza?
La somma, scusi. C'ha ragione.
Ah, ok.
Sorry. Here, there's a plus sign. Thank you. So we don't really use, well, we don't have a use for this. Well, we do have specific volumes here and pressures, so that's good. But what are we going to do with these jump in these static enthalpies? One thing that is interesting to note, however, is that whenever you do these, always think, what kind of assumptions did I make? And in this particular case, I never used the equation of state. So I haven't used any equation of state, so I haven't even used the perfect gas equation of state. So that means that this last statement, okay, this sort of last thing that I wrote is really universal in the sense that it can be used not just for gases, but it's independent of any equation of state. So in fact, I'll just state it here, but if you are interested in things like propagation of detonations, okay, inside explosives, so inside solids, and this is, again, something that is used, okay, in, well, explosives are used, for example, in many applications, not just in terrorist attacks, but also in mines, for example, and demolition and things like that. The exact same equation can be applied also for solids. Now, we're not going to be interested in that for the time being, but I'm just saying that always look for the assumptions, because in this case there aren't any, okay? And so this can be applied independently of the equation of state, okay? So also for solids. Now, we have to be careful here in the sense that across the wave, okay, so by looking at this difference in static enthalpies, across this waves, there is going to be a reaction, okay, of some sort, a chemical reaction. So there's going to be a release of heat. So how do we express this? Because it's an exothermic reaction, right? So generally speaking, for any species, so I'll just write down here for the ith, okay, species, the static enthalpy is a function of temperature, and will be equal to, so we've seen this many times, standard heat of formation, which we can call like delta HF, okay, of formation of the species I, which is generally taken at a reference temperature, okay? I can even add here the standard state, but it's immaterial, or it's not influential, because we know that, remember, for enthalpy, there is no mixing, okay, enthalpy. So the standard state will be equal to the actual value. Plus a sensible energy, a sensible term, which is essentially the integral from the reference temperature to temperature T, okay, of the specific heat at constant pressure, okay, for the species that we're considering, species I, which is generally a function of temperature in dT. Okay. Okay. So again, because we have the upstream and downstream here enthalpies, okay, we can write down these expressions for the unburnt, okay, side, which was going to be some heat of formation, sorry, of the related to a mixture, okay, in the upstream case, plus, now, we're going to make an assumption here that Cp is constant, okay, so it's a crude assumption, but this allows me to write down this very simple equation. So we assume for the time being that this is a simplified, okay, theory. So Cp is constant. Now for the burnt side, we have just about the same thing. Okay, Tb minus T ref. So this allows me to actually represent the difference, okay, of these static enthalpies, which is what? Well, the difference in heat of formation, which has a very specific definition, which I hope you remember, plus Cp, okay, Tb minus Tu. Oops, Tu. Okay? If you remember, the difference in heat of formation is exactly the heat of reaction. Okay? Which we're going to be giving here a minus sign to this, okay? In the sense that we know that, so if we consider Q, let's call it QC, okay, the heat of reaction. Q is positive. We're going to give it a minus sign so that we remind ourselves that this is a exothermic reaction, okay? So delta H is negative. Plus, again, Cp Tb minus Tu. Okay? So this is where generally this treatment is really different from the classical gas dynamic kind of treatment, because we have essentially this term here, okay? A release of heat due to chemical reactions, okay? So now what we can do is very simply take this expression and substitute it. Okay, so minus QC plus Cp Tb minus Tu, and substituted in the Hugoniot expression, which we wrote up here. So it's equal to 1/2. So that's Vb plus Vu and Pb minus Pu. Okay? So that's the general expression for the Hugoniot curve. Now, clearly, it's not in the right kind of form, especially because we have Tb and Tu, so the temperatures up here. So we have to get rid of those temperatures if we want to rewrite this in terms of P hat and V hat, okay? And so I'm not going to do this because it's tedious and I'm not requiring you to know all the steps. What I will require is essentially, well, this definition here in the sense that we have to remember what Q is. So this is the heat of reaction. So it's the heat essentially released. The Q is essentially measured in kilograms, in the joule per kilogram. Okay, so we're going to, because we have, we're going to have to transform this relation here in non-dimensional variables. Okay, there's going to be a QC, which is essentially the non-dimensionalized version of QC, which is QC divided by PU over rho U. Okay. Remember that Pu over rho U, P over rho is essentially RT if we use the equation of state for gases, okay? And this is again in terms of joule per kilogram, okay? This right-hand side term. So this is non-dimensional, okay? But it's going to represent in non-dimensional terms the heat of reaction across this combustion wave. Now, let me skip, okay, a few steps, okay? We're going to use essentially all of this expression, and we're going to transform it in non-dimensional terms as follows, okay? I'm going to be using relationships like these. R over Cp is equal to gamma minus 1 over gamma, okay? And after 5 or 6 steps, we have this expression here. So what's important is to understand the general form, okay, of this expression here. Okay? So you see that on the left-hand side, okay, we have a nonlinear function, okay, of P hat and V hat. Then we have a constant. Gamma is clearly the ratio of the specific heat, so it depends essentially on the gases itself. Okay, this is a squared plus 2qc hat gamma minus 1 over gamma plus 1. Now, what is this Hugoniot? So you can put a box around this. So this is the final expression of the Hugoniot curve. Okay. So what is this Hugoniot curve? How does it look like? Well, if you look at it, it's in the form essentially x minus x0, y minus y0, okay, equal to 1 minus x0 1 minus y0 and then a constant. So that's the general form of what the Hugoniot curve is. Okay? And it's an hyperbola. Okay? It's a hyperbola that has asymptotes in x equals x0 and y equals y0. Okay? So what does that mean? If we look at this particular case, in this particular case, we have that the two asymptotes, okay, on this plane, on our usual v hat plane and p hat plane, will be essentially this one, which is v hat equals this value here, gamma minus 1 divided by gamma plus 1. Okay? And then this other asymptote will be over here at the value p hat equals minus gamma minus 1 divided by gamma plus 1. Okay? So these are the hyperbola. Now, obviously, and this hyperbola, if there has another...
Scusi, professore, ma quindi nell'espressione
Questa qui è più, ovviamente. Io ovviamente i più e i meno qua, ragazzi. This is P plus, okay? Because clearly this is going to be a minus, okay? And so on. Is that your question? Quella domanda?
Sì, grazie.
No, i segni, come avete visto, diciamo, mi interessano poco, non è quello l'importante. Anche se poi, vabbè, con un segno meno ci si fa cadere, voglio dire, ci si fa esplodere un missile, un lanciatore. Allora, cadere un aereo. Allora, when C is 0, okay, the hyperbola essentially passes through 1, 1. Okay, you can verify this. Okay, and so using this expression here, right? And so essentially, when QC hat is 0, the hyperbola will pass by 1, 1. So what we have is the following. So I'm going to try and draw this, but clearly I'm not guaranteeing anything. So this is an asymptote. This is the other asymptote. Okay, I mean, you will draw it much better than me. I mean, I really can't with this thing. Okay. So essentially, this curve here is the Hugoniot when there is no heat release. So now, in some sense, I want to tell you that, so this is 1, 1. Whatever you've done, say, for example, in gas dynamics, okay, if you've done gas dynamics, is you will recover everything you know about, for example, shock waves, okay, when you substitute essentially QC equals 0. Why? Because there is no heat release. So it's a sort of a cold wave propagating. And so you will essentially recover all of the results that you know about shock waves, okay? On the other hand, if QC is different from 0, we have these other hyperbolas, okay? Which will not pass by 1, 1. Okay, so it's a family of hyperbolas which are essentially displaced away from 1, 1, okay, in this direction. So essentially, there is a line here, guys, indicating that this is the direction of increasing heat release, okay, across the combustion wave, okay? Now again, let me just repeat this. So when QC equals 0, you will essentially go back to the Rankine-Hugoniot jump relations for a hydrodynamic shock. On the other hand, as we will see now with the intersection with the Rayleigh lines, okay, when QC is different from 0, it's bigger than 0, we have a whole new different kind of family of solutions, okay? Now, before we do anything, please let me just, because I should have prepared this before, let me just stop the sharing for 1 minute, okay? I'll go back, okay? I just need to recover sorry, I just need to recover a picture, which is absolutely impossible for me to draw on this blackboard. So this, by the way, is the most complicated picture that you will, that you will have to draw in this course. I usually have trouble drawing it also on the blackboard. And I'll show you why in a second. So now what we have to do essentially is the intersection between the Rayleigh lines and the Hugoniot curve, okay? So I'm going to recover this. Oh, maybe I do have it. No, I don't. Oh, how nice. Well, you have to be patient because it's on the Google Drive, which is not working. So let me just close everything. Oh. Okay. Okay, you will find this in the notes. Ah, here it is. Beautiful. Okay. So let me reshare. Can you hear me? Yes, you can.
Sì.
Here. Okay. Can you see a picture here?
Sì, si vede.
Okay. So what are we looking at here? Well, we're looking essentially at the intersection now, okay? Of the Rayleigh lines. Can you see the little mouse?
Sì, sì.
Okay, perfect. So this is the PV plane, okay? This is the 1, 1, okay, the origin, which represents essentially the upstream state. You can see here, there is a supersonic Rayleigh line over here, and there's a subsonic Rayleigh line over here, okay? Now, let's start by looking at, and also the Hugoniot hyperbola, okay? Now, let's start by looking at the QC equals 0. Now, what I suggest you do is you practice this a couple of times with a pencil, okay? It may seem strange, but it's a little tricky to draw, okay? you never get the intersections right. So this is clearly the forbidden zone here and here, okay? So let's start from QC equals 0. So this is essentially what you have with a classical hydrodynamic shock. So no, absolutely no chemical reaction, okay? So suppose that you take the intersection between the cold shock here, the cold Hugonio, and the Rayleigh line, okay? We're going to have this solution here. Can you see this? Sorry, I have to. Now, this is your classical hydrodynamic shock solution. So in this sense, if I give you now the upstream conditions, PU and rho U, or PU and VU, okay, you'll be able to read in this point the non-dimensional values P hat and V hat. So PU over PB and whatever. So you're going to recover the burnt side quantities, PB and rho B. So the pressure downstream of the shock and the density downstream of the shock. And we're going to recover essentially the Rankine-Hugoniot jump relations, which you may or may not have seen. But and you can have them, for example, tabulated, okay, as a function of the Mach number. Okay. Now, what's the Mach number here? It's the slope of the Rayleigh line. Okay. So if it's a little bit less supersonic, okay, these are supersonic clearly slopes. Okay. You can see here. So these are the Mach number mu bigger than 1 slopes. Okay. And if it's a little less supersonic, okay, the slope is going to be a little less, but still supersonic, so still bigger than 1. So we're going to move along the Hugonio here, okay? As you can see, it's a situation where there is a dominating effect of compression, okay, an increase in pressure, rather than a decrease in specific volume or an increase in density. Okay, so the dominating factor here across this shock wave is the increase in pressure. So I hope that's clear. Okay, now it is also true to some extent that the Hugonio curve extends all the way down here. So in theory, you could also have a subsonic intersection. Okay. Now it turns out, and we're not going to prove this, okay, rigorously, but it turns out that these solutions, okay, they're the so-called strong solutions. The farther away you move from the origin, the stronger the solution is, simply because the downstream values are going to be very different, okay, very far from 1, okay, with respect to the upstream conditions, okay? So that's why it's called strong, okay? The closer you get to the 1-1, so the origin, okay, the closer you get to the upstream conditions, and so essentially there's not going to be a big change between downstream and upstream, and so you call them weak solutions. So let's go back to the subsonic solution. You see that in theory there is also going to be an intersection between the Hugonio and the Rayleigh line somewhere here, right? Now, this is even wrong because this would go on the negative side of pressure, but suppose it's on the positive side, it could, in theory, be a physical solution. It turns out that these strong solutions for subsonic waves, okay, do not exist. They're not physical, because even though they, in theory, guarantee conservation of mass, momentum, and energy, okay, they would imply across them a decrease in entropy. So if you calculate also the entropy, okay, they would be sort of involved with a decrease of entropy, okay? Which cannot be the case. So they are unphysical, okay? But I'll get back to this, okay? Now, this is for QC equals 0. Now, look what happens if QC, okay, the heat release across the wave is non-zero, it's in fact positive. Then the Hugoniot curve that you're going to have to see is this one here, okay? I hope, is it clear? I mean, are you clearly seeing or is it confused?
Sì, sì,
Si vede bene, diciamo.
sì, sì, tranquillamente.
Okay, so this is the solution that we have to look at. Now, as you can see, the intersections between the Rayleigh lines and the Hugoniot curves, in this case, are 2 intersections, okay? In the supersonic case, and so it would seem also 2 intersections in the subsonic case. So that's pretty interesting because now we have a completely different scenario with respect to the classical hydrodynamic shock scenario. Now we have 2 couples of solutions, okay? Again, I'll repeat it, one for supersonic propagation and the other one for subsonic propagation. So there are 2 couples of solutions, okay, that are compatible with the conservation of mass, momentum, and energy. Now, the supersonic solutions we're going to call detonations, and the subsonic we're going to be calling them deflagrations, okay? Now, this is a completely new phenomenon, and just by paper and pencil, we really found out that physically there can be 2 solutions. So 2 ways in which a combustion wave can propagate through a combustible mixture, self-sustain itself and release energy, okay, at the same time, okay, in a steady state scenario, by the way, okay? So we haven't solved any time derivatives of anything, okay? It turns out that experimentally, this is the case, okay? Experimentally, I can reproduce in a flammable mixture. So if I mix some, for example, hydrogen and oxygen in a controlled environment, okay, I can reproduce extremely fast and extremely powerful supersonic solutions called detonations, which can involve a very large increase in pressure, okay? But at the same time, the same kind of combustible mixture, okay, can be burnt, essentially consumed, much slower, okay, through what we call a deflagration. Now, deflagrations are what we typically know as flames, as premixed flames. So it's what you get, for example, when you cook your pasta on the stove. We can stabilize the subsonic combustion wave in your kitchen, and that is what we call deflagration, okay? So that's essentially the picture, and it's the most sort of important first thing that we can conclude from this picture that you're looking at, okay? Now, I will tell you that as far as deflagrations are concerned, so the subsonic solutions, the strong solution, which you can see here, again, let me repeat, there are 2 solutions, 2 intersection. One is going to be closer to the origin. So that's the weak solution, simply because we consider weak as a smaller change from upstream to downstream, okay? Because remember, these non-dimensional variables are the ratio of the upstream and downstream, okay? So if it's closer to 1, it means it's weaker, okay? Now, clearly, this is farther from 1. So it's the strong solution. Now, also for deflagrations, as well as for non-reactive waves, these do not exist, okay? They are unphysical. So I wrote it here, they're unphysical because if we compute the change of entropy will be a decrease, okay? I'm not going to prove this rigorously, we don't have time, okay? But suffice it to say, there is no such thing as a strong deflagration, okay? So a premixed flame essentially that has this sort of huge increase, okay, in specific volume, so a huge decrease in density, okay? The decrease in density is going to be of the order from 5 to 10, not more, okay? So we only have, as far as deflagrations are concerned, these solutions here, okay, which are essentially your weak deflagrations or premixed flames. Now, on the other hand, detonations have two solutions here. A weak detonation, which is over here, and a strong detonation, which is over here, okay? And that's just about the story that I want to tell you now. We'll get to the details in a second. So I'm not going to repeat this thing on the blackboard because I would never be able to draw it, okay? So I hope you've succeeded in drawing this. So practice a little bit. You can even use MATLAB, okay, or something if you want, and look at it on an sort of an exact way, okay? If not, just write it or draw it with a pencil, okay? One other thing, okay, that I'm concerned about here is, well, look at the detonations, okay? There are two solutions again, but there is a particular, if you look, value of the Mach number, so the slope of the Rayleigh line, where essentially the strong solution and the weak solution, after having gotten closer and closer together, they coincide. Can you see this? This is called a Chapman-Jouguet point, okay? Or upper CJ point. Chapman-Jouguet, okay? And it's over here. And it's where essentially the Rayleigh line and the Hugoniot curves are tangent. It turns out that's going to be a rather important point as well. As you can see, I'm concentrating a little bit more on detonations rather than deflagrations. There is a particular reason for this, because this Rayleigh Hugoniot approach is extremely useful and accurate for detonations, a little less accurate for deflagrations. And by this time, you should know why. Because, and I told you already at the beginning, it's because we're looking at the wave from very far away. So essentially, we're looking at the far upstream and far downstream states and looking at how they can be compatible through essentially the conservation of mass, momentum, and energy. But we're not looking at the inner structure of the wave itself. It turns out, because deflagrations are in fact propagating through a diffusive process, that you really have to look inside the inner structure of a premix flame in order to understand how it propagates. So it will turn out that the Rank-Hugoniot I said really good. Rank-Hugoniot approach will be less useful for deflagrations. Okay, and we have to build another accessory theory, okay, for laminar premix flames, okay, which is a little bit more useful. But one thing at a time, okay? So let me just stop sharing here and go back to the blackboard, the whiteboard. Can you see it?
Sì.
Okay, so what can we do with this analysis, okay? Well, we have concluded that essentially intersection points, okay? Intersection points between the Rayleigh line and the Gonio curve are physically let's say admissible or compatible, admissible values of p hat and v hat. So p hat is pb over pu, and v hat is vb over vu, right? So how can we use these values? Okay, these are exact numerical values, okay? Then they're admissible. And there's 4 of them, okay? Because we've seen it's 4, and some of them are, one is in particular is unphysical and so on. So that means that we can find those, again, if we know certain constants or certain parameters. What are the parameters? So if you go back to, so given certain parameters, what are those parameters? Well, if you look at the Rayleigh lines and the Gonio curves, you'll realize there are at least 3 basic parameters that we need to specify. Well, one is gamma, okay, which is Cp over Cu, Cp over Cv, sorry. Which is the nature of the flammable gas, essentially. Okay, if it's monatomic, if it's diatomic, so on and so forth. Okay, so gamma, 1.23 or 1.31. Okay, it's a constant. Okay, in this particular case, this is a simplified kind of scenario. Another thing that appears in the Rayleigh lines and in the Gonio curves, and particularly in the Gonio curve, is QC. QC, okay? The heat release parameter. You can call this the exothermicity, okay, of the flammable mixture. It depends on the mixture. It also depends on the composition of the mixture, right? It depends on, for example, the equivalence ratio. And it depends also, obviously, on the fuel and oxidizer. Okay. What other constant do we have? Well, look at the Rayleigh lines. Okay. I won't go up. But really, there is a parameter that has to be specified that it's the actual propagation Mach. It's the actual mu, or the upstream Mach number. Now, that may seem a little disappointing in the sense that you may ask, well, doesn't this whole treatment give me the propagation speed? Well, no, generally it does not. You have to specify it because you have to specify the slope, okay, of the Rayleigh lines. However, this is not totally true. There is one special case where you can have mu you can actually derive mu from the analysis and not specify it. And this is when the radii lines and the Hugoniot curves are tangent, because if they're tangent, fortunately you have an extra condition of tangency, okay, which can be used to actually find out mu. And we will see that at least for detonations, this tangent condition is really important, the CJ condition, okay, the Chapman-Jouguet condition. It's important because, in fact, most, if not all, of the detonations that you can actually reproduce, okay, naturally or in a laboratory are, in fact, these kind of degenerate or special cases, CJ, okay? So they are, in fact, the ones that can be observed in nature, okay? So it's not a particular case, in fact, it's the general case. And I'll also tell you why that is the case. It's a little less useful for deflagrations as usual, okay? Because, and we will see that this numerically at the end of this, let's say, overall treatment, because the kind of Mach number that we get for detonation, deflagrations, imposing the tangency condition is really wrong. Okay, it's an overestimation of what actually premix flames speeds are. Okay, but we'll get one step at a time. So, what do we do with this Rankine-Hugoniot analysis? Well, suppose that I give you, given the upstream conditions. Okay, so suppose that I give you the unburnt pressure, okay, the unburnt specific volume, and the upstream Mach number, okay, and also constants like gamma and the exothermicity, okay. The Rankine-Hugoniot analysis essentially determines, okay, the downstream conditions of pressure, PB, and density or specific volume, VB, okay? And of course, given PB and VB, also the temperature, okay? So I'll write it here. So actually PB is divided by R and then rho B, sorry. Okay, so I'll derive essentially pressure, density, and temperature downstream, which is clearly not a little thing. I mean, given any upstream condition, I can give you, if they exist, okay, the downstream conditions, okay? But you also have to specify, unfortunately, okay, for the general case, you have to specify also the upstream speed or of the flow or the Mach number, okay? So let me try and recap some of the things that we have seen, okay? So, so we've seen that, let me just try, okay, and draw at least a simplified version. So we have 4 solutions, okay? Okay. 2 are supersonic, okay? and are called detonations. So these are the supersonic solutions, okay? One is a strong one, okay? A strong detonation, okay? And the other one, closer to the origin, is a weak detonation, okay? Both of them, okay? The upstream Mach is supersonic, okay? Now, as far as the subsonic solutions, okay, we have a weak deflagration, which we call a premixed flame, okay? In theory, we could also have a strong deflagration, but this is unphysical. Okay? And in any case, these are both for the upstream Mach number smaller than 1, so subsonic, okay? Generally here, strong detonations, okay? Let's write it here. You have essentially a very, very strong compression, okay? And for weak deflagrations or premixed flames, what we have essentially is a strong increase, okay, in specific volume. So we have a strong decrease in density. Okay, let's say of the order of 5 to 10. Okay, so up to 1 order of magnitude. And this is clearly the scenario, okay, for when the, how can I put it here, when the gonio curve, okay, is a reactive curve. So it essentially has a non-zero value of the heat release. So QC is bigger than 0, okay? Again, let me repeat, if QC is equal to 0, you would only have the strong solutions. So you would only have essentially the strong solution here, okay? Now, as far as the deflagration is concerned, okay, again, this will be a strong detonation, deflagration, and this is unphysical, so this doesn't exist. But this, okay, for QC equals to 0 is a hydrodynamic shock wave. Okay? So this is the long story short. Next time we're going to be talking about these special solutions that are the tangent solutions. Let me try and draw this. So there is a particular Mach number, you see mu, where there's only one, okay? Solution. We can call this point here U, the upper CJ solution. So we're going to be talking about these just so that it's clear as the Mach number is decreased here. So the slope of the Rayleigh line is decreased. You see how the strong detonation moves towards you and the weak detonation moves up towards you. So in fact, what U represents it represents the weakest of the strong solutions, or the strongest of the weak solutions. I don't know if you can see this, okay? Because the weak solutions live essentially from here to here, and the strong solutions from here to here. But as the strong solution moves down, it weakens, and as the weak solution moves up, it strengthens. And so we have that U is, again, the strongest of the weakest, and the weakest of the strongest of the strong solution. Yeah, I guess that's all. I'm going to stop here, otherwise I'm going to say too much. You may be asking, okay, but what is the structure of these solutions? Well, let me just say one word. As far as flames, so subsonic solutions are concerned, you will see them essentially in another theory, okay, which is the laminar premix flame theory. As far as detonations are concerned, the inner structure, which is not clearly in any way revealed by the Rankine-Hugoniot theory, can be at least in some way conjectured, okay? And there is a very, very good conjecture, okay, which is called the Zeldovich-Neumann-Düring conjecture that we're going to be seeing, that really visualizes the detonation as an initial shock wave. It's like a completely non-reactive shock wave whose role is that of compressing the flammable mixture and heating it up. So when you heat up the reactive mixture, what you've done is you've increased essentially the reaction rate. So now the flammable mixture can in fact react, and it will react like a thermal explosion in some sense. So it's going to be an advected thermal explosion, like the Semenov system that we've seen, okay? Again, these are all things that I'm anticipating, so I'll do them next time, okay?